thereby giving you a higher output for less energy. So the heaters are installed in these heater wells. They're for a kilometer in length. This is typical of what's done in the, say, D wells, for example, in Canada, about 300 meters of depth and a kilometer of heated section. And then there are production wells that are spaced between the heater wells, but many fewer production wells than heater wells. And the heat goes in by thermal conduction only. The heaters are extremely hot, but the average formation temperature rises only by superposition. So over a period of 3 years, you get to the retorting temperature, and the oil basically gets produced as a vapor through the production wells. Now, why does the oil get produced as a vapor? It's because this process basically cracks the very long chain molecules of the kerogen into carbon number chains that are no more than around C20. At 300 degrees centigrade, with the low pressures we operate at, these are all in the vapor phase. So the reservoir basically depletes as a natural gas reservoir. And the products that are made are extremely light. Most of the coke that's associated with the kerogen stays in the ground. So it's a type of carbon sequestration process. You can actually see the carbon form and stay behind when you pour after the pyrolysis operation. You can see the surfaces of the carbonate that turn jet black. What's nice about the in-situ conversion process is that it has a very high energy balance. And it generates very high value products. The oil is extremely light, and the gases have a lot of liquid components associated with it. A lot of LPG, a lot of hydrogen, which is extremely valuable. And we've designed it over the years to have as small a surface footprint as possible. The entire project over a 30-year period uses up less than 1 square kilometer of surface area cumulatively, including all the surface facilities. Now, one nice thing about this technology is that the heat source is so flexible. You can use electric heaters, you can use downhole gas heaters, you can use heat transfer fluids like molten salts to transfer the heat. And you can start with one type, which is the type I've spent most time working with, which is the electric heater. Very technically mature. This thing is about 1.5 inches in diameter. It's got a core that's made of a curing metal that self-regulates at exactly the temperature you want, so it can never overheat in the subsurface. And then it's got a magnesium oxide core and a stainless steel sheet for corrosion resistance. And these things are made up continuously in mile-long spools. You spool them into the horizontal well and then spool them back out when you're finished. The only thing that's negative about the electric heater is its fossil fuel to heat efficiency. Because you're going through a turbine step that's converting the fossil fuel energy to electricity, it's only about 45 to 50% efficient. So that's a negative with respect to things like carbon dioxide emission. And so then we've also developed at Shell this type of gas heater. These things are spaced every 50 feet in the horizontal section. They work on natural gas. And you would think that because the gas is actually burned in the well, in the horizontal section of the well, that it would be 100% efficient. But it isn't, because you need so much air to be compressed and sent down the well to combust the natural gas. You wind up with compression costs that eats up a lot of your energy. Overall, this is only about 60% efficient. So the technology that we're now working on is what's called the heat transfer fluid. It's a liquid that's heated up at the surface using a natural gas furnace. That liquid is sent down the well and then back for reheating. Here you don't have the compression cost. And if you use a material called molten salt, this material basically can go up to 600 centigrade, has extremely low vapor pressure, a viscosity close to water, It's optically clear and has a tremendous heat capacity. So you can go a kilometer in length and come back. You have very uniform temperature wherever you left. We're developing this type of heater technology in the United States. The design is being built by Southwest Research Institute in San Antonio. And we should have the first version of this available for subsurface use. It's actually a widely used technology both in solar plants and in chemical plants whenever you want really uniform high temperatures. It's never been used in the subsurface. So what's exciting about it is that we can achieve between 80 and 85% efficiency and never have to make use of electrical power. And it couples extremely nicely to renewables. Many of the solar plants use this type of molten salt for storing the energy overnight when the sun is down. And in that case, you approach 100% energy efficiency. It also fits in nicely with places that have a large amount of wind electricity, where you can again store the energy in the molten salt. Now, in terms of testing the technology in the field, very first deployment was done in Sweden from 1940 through 1961. They produced about 500,000 barrels from their oil shale using electric heaters, vertical electric heaters. And I visited their site in Gaventorp. It got me really excited about the potential of the technology. One thing I didn't like about what the Swedes did was they had the heaters very closely spaced together, and they heated to too high a temperature, 400 centigrade, which is already starting to decompose the carbonates, and you're starting to get carbon dioxide out. So I wanted to operate no hotter than about 300 to 325 centigrade where the carbonates are stable. And that set a spacing of roughly 40 feet between heater wells. And over the years that I worked on this at Shell, we did over 7 pilots. They're all vertical pilots because you want your wells to be very accurately drilled. So this is the Mahogany Demonstration Project South with 16 heater wells and 2 production wells and various monitor wells. And here's the results. There's the oil. There's the gas. It's about 1/3 gas, 2/3 oil. And the data is actually shown here. That's the field data. This is a numerical simulation that's not a match. It was actually done before the pilot was energized, similar with the oil. It's possible to numerically simulate what's going to happen with extremely high precision because the heat only goes in by thermal conduction. No fluids are injected, no hydraulic fracturing. Just put in heaters and let the heat diffuse in. Once you know the thermal conductivity of the rock, you can predict exactly how long it'll take to get to pyrolysis temperatures. Now, the same technology works in the other main resource, the tar sands. And here is a horizontal well system. Here we have 18 horizontal wells that go down and off to the side underground, and 3 production wells here. And we operated this at our Peace River field from 2004 to 2008. And we produced over 100,000 barrels of oil that look like that, about 30 to 49 degrees API gravity. This is from a field that has always produced a tar, a molasses type tar, about 8 degrees API gravity. And the reason I show this is because this is what the surface footprint looks like in a horizontal configuration. You basically continue this along the rows of heaters, the row of the production well, and that is it. That's the surface facility. So you can see that you don't use up very much surface footprint with a horizontal well configuration. Even though on the subsurface your heaters are going out kilometers in either direction, your surface footprint is very small. Now, what's going on during the actual heating process is very important because there are several things that are going on. You're getting to pyrolyzing temperature where the thermal energy is cracking the bonds, typically the carbon-carbon bonds, but in the case of the Israeli Kerogen, it's the carbon-sulfur bond that breaks first. And that in turn